welcome to RF transceiver design course. Up to now we have discussed about various basics aspect, and we have already discussed about transceiver architecture. Now in this lecture, in this module, we will try to cover the active devices that are widely used for RF and wireless application, and this is a comprehensive study, and if you are interested more in detail, you can go through the basic of the devices course, then you will understand more in deep. So let us start the active devices, the portion of active device module 4 on RF transceiver design. So without active devices we cannot design any amplifier or any circuit, and there are various device technologies that are explored up to now in literature and in use, and various industries are associated with it for wireless communication system. So there are basic classification that can be done. So it is based on two material that mostly used, two semiconductor material. One is a silicon based and another is 3V compound semiconductor based devices. So based on which material, base material is used, we can classify it broadly. So if we go into the silicon based and 3V compound semiconductor based device, what are the basic difference that we will try to see one by one. So as we know that silicon is available abundant, and it is very low cost, and the high we can have very high volume production. We all are using CMOS technology, and which is high, we can produce in more number of chips by using silicon based technology, and it has improved frequency response also over the years. So we all know the Moore's law, and based on the Moore's law we are growing, reducing the length every decade, and because of that our frequency of operation is improved. However, in 3V compound semiconductor, it has advantage of their intrinsic material property, because it is a wide band gap material, and the performance is superior in terms of power and voltages in high frequency application. So mostly MMIC it is widely used, and silicon based technology, it is a very well established manufacturing infrastructure. So there are giant company like TSMC and Intel and all, they have a well established manufacturing infrastructure. And however, 3V compound semiconductor has a limited manufacturing capability and types of, it is mostly used for particular application. And in silicon based there are two major types depending on their physical carrier transportation. So how the carrier transportation happen, based on that we can identify the two mechanism. One is a unipolar, that is a FET devices, and another is a bipolar junction transistor, that is a BJTs. So these both can be come into the silicon based device technology. However, by using the compound semiconductor, we can have a gallium arsenide based MOSFETs, gallium arsenide based HAMT, high electron mobility transistors, and indium phosphide or PHAMTs. There are gallium arsenide based HBTs and similarly indium phosphide based HBTs. So these are the rough broadly that the type that we have added here. Now if you see in terms of in silicon, there is a BJTs, mostly widely used silicon metal oxide semiconductor FETs, LDMOS for high power application, and then silicon germanium heterojunction bipolar transistor. So these are the devices that can be made by using a silicon technology. So this is a broad category if you are interested more in detail, you can go for silicon based silicon based devices or compound semiconductor based devices. Based on the application and your requirement, you can choose the devices whatever you want to design. Now, we have seen here unipolar and bipolar junction transistors. So, what is the basic difference? Because as here written and as I told, this is a well established manufacturing infrastructure and widely used. So, these are the two basic types, unipolars, FETs and bipolar junction FETs, which is come under silicon based devices. So, what is the basic difference in terms of this terminology unipolar and bipolar? So, FET devices are referred as a unipolar. So, because this has the majority of carriers are responsible for the transport characteristics, and drain current in FET is modulated by. So, we all know that the gate will modulate the current. So, through a channel with modulation scheme, and the amplification process in FET is characterized by transconductance, that is a GM. So, this is how the unipolar device work, and if we see about bipolar devices, that is why BJT is called bipolar junction transistor, that carrier transportation mechanism in bipolar transistor involve both electrons and holes, and the minority current injection from the base modulates the collector current. So, it is mostly named as a current controlled device, and however BJT is a voltage controlled device. So, that is a basic difference in terms of analogy unipolar and bipolar, and that is why in BJT we consider the current gain. However, in the FET we will consider the transconductance, because output is a current and input is a voltage. So, this is the basic difference between unipolar and bipolar. Now, when we talk about the semiconductor, then there are base materials. See, these are the 5 base material that are widely used, that is a silicon, germanium, gallium arsenide, gallium nitride and indium phosphide, and each is dominating in their area, means it is each material has a specific application and it is used for making a devices for RF application. So, we will go one by one, we will discuss about each. So, if we talk about silicon and germanium, silicon has a higher thermal conductivity, but the electron drift velocity and mobility are slow. So, this thermal conductivity will help to release the high power, due to high power the high temperature is generated, and I already have given example when we discuss the noise, that noise is proportional to the temperature, and that is why when we have a processor in our computers and that processor has a fan or some cooling mechanism is required, so that this power will be easily this thermal energy, which is a temperature, can easily be dissipated in the air and you can cool down the your processor, and it has a electron drift velocity and mobilities are slow. It is a lack of semi-insulating substrate and it has a additional development costs. So, semi-insulating substrate are important if you would like to design a very high end passives. Now, this high end passives, that means if you want to make a inductor or high end passive like transmission lines or couplers, which required a very high Q, and in that case you required a insulating substrate. So, however, in silicon technologies it is a drawback, and that is why the Q on chip Q of inductors are less. and semi-insulating substrate are easily prepared in most compound semiconductor. That is the advantage of using gas or GaN for many RF application, where you have a more passives than the active component. And this property is beneficial in terms of providing a RF application with a high device isolation and low dielectric loss. So, the isolation between, because we have multiple frequency components, as we have seen in the last class in the architecture, if this is a mixer, it has a three frequencies involved. One is a RF, then there is a LO, and there is a IF. So, these three frequency, if there are not enough isolation, then it is difficult to make the high performance RF. So, that is what is related to silicon and germanium. Now, if we see the same thing for gallium arsenide material has a high electron mobility, which help us to design higher power, high performance RF chips compared with the silicon, and it has been choice for MMIC application for decades. It is widely used, and in future also for getting the very high performance RF MMIC, it is going to use. But what is a drawback? It has a poor thermal dissipation capability. So, this is while designing the power amplifier, or when we design a very high power circuits, at that time there is a special thermal analysis needs to be done, and that uh, because of this poor thermal dissipation capability, sometimes it applications you are also limited. It has a high thermal resistance value in RF power application is harmful, and special care must be taken to mitigate the thermal related system performance degradation in gallium arsenide. So, this is about the gallium arsenide. So, there are for many high performance receivers, mostly let us say for satellite application, or where you required a precision in the terms of sensitivity, in that kind of application these gas based receivers are used, and in certain cases where the power high power amplifier also can be designed. Another class is GaN, which is dominating in terms of power amplifier market, and it is another market that is high voltage application also. So, what is the advantage? It is the fastest drift velocity among all other semiconductor material, and the wide band gap in GaN translate to a higher breakdown voltage. So, you can supply a very high voltage. So, that is why it can be a choice of in charging application, in many high power high voltage application also it is useful. And in RF, mostly the high power RF transistors or high power amplifiers it is used, and it is also low thermal resistance, and possible epitaxial growth on silicon carbide substrate make this material system perfect for a high power RF application. So, because of this silicon carbide substrate, it can provide the means thermal low thermal resistance, and the temperature will easily dissipate, and that is why it is widely used for high power RF application. Now, indium phosphide, it has been widely used in semiconductor based optoelectronics for decades, and this will ease the problematic thermal issue as we have seen in gas to some extent. So, that is the advantage here also, and they can yield the fastest transistor among all the semiconductor device on both FET and HBT devices. Even indium phosphide based HEMT can also be used for at a superconducting temperature also, it has a wide application, and indium phosphide have been sought to become a technological alternative for gas based material system due to their superior intrinsic electrical property. So, each device, each material, semiconductor material has their specific application, and it is widely used according to their uh, properties. So, these are the listed properties that we have discussed, but if you are interested more in detail, you can go through the references that are provided at the end of the slides. Now, if we have seen a difference in the unipolar and bipolar. Similarly, if we want to compare the FETs and HBT, that is heterojunction bipolar transistor technology. So, that because these both are going parallel in the many RF application, and when we are talking about millimeter wave or high power application also HBT or BJT is used. So, we will see one by one what are the comparison on HBT, BJT, and narrower base and thinner collector in a bipolar device can decrease the carrier transit time, and the vertical layers in HBT are defined by the epitaxial growth. Commonly available crystal growth techniques, precise epitaxial growth will help us to make these vertical devices. And the FT, this is very important. The FT and Fmax is in the range of 100 to 300 gigahertz range, and can be achieved with the conventional 1 micrometer photolithography technology. So, even 130 nanometer can provide 300 gigahertz FT, and that because of that this can be one of the choice for sub terahertz application, where many futuristic technology can be developed. And HBTs intrinsically have better device matching and are suitable for different pairs, because BJT has input impedance which can easily be matched. Now, we see about FET, it has a shorter gate length in FET, can reduce the carrier transport time. The gate length is here defined by photolithography, and we all know that length every decades are reduced, and we are getting a high performance, and every 10 years there is a double number of transistors on wafers are increased. So, the high performance submicron FET demands advanced photolithography, because you are going to small and small length. So, the photolithography requirement is crucial here. A gate length of less than 0.15 micro in FET will be required to achieve a comparable RF performance regarding larger FT and Fmax. So, it is always challenging for RF designer to design a RF circuit in higher node technology, because the FT and Fmax are limited for higher node. That is why we need to move for lower node technology. Then it is a prone to mismatches. There are more process variation and channel formation. So, yield is not that much high. So, the amount of active means working chips are less, that is one of the disadvantage of this technology. However, it is cheaper compared to HBT or BJT. So, in HBT again there is a higher current density than FET devices because of larger emitter area than a thin channel in FET. The current density with a small voltage of input, you will get a large current. HBTs can handle a more power within a smaller chip size than the FET based power circuits. So, HBT can be also used for high power application, if for application like beam forming and multiple antenna technology if we are planning to work in high frequency application. The breakdown voltage of HBT can be tailored for optimized power performance via epitaxial growth, and for a BJT the noise figures are determined by a short noise related to the operating current, that we already have seen while I discussed the noise in detail. And very complex device level fabrication, it has a multiple etching and metal deposition steps. That is why the cost of this process and the amount of production is limited. However, in FET it is a high. The breakdown characteristics of FET is affected by the lateral device dimension such as gate to drain, and that is why there are some technology like LD MOS are available to improve the power capability and breakdown characteristic. In general, FET has a better noise performance at higher frequency. The noise source of FET are mainly the thermal noise and suitable for low power LN application, but it has a flicker noise also that we have already discussed, and it is simple to fabricate, require not more than 3 to 4 masks for a device. So, these are the basic comparison. At some place BJT HBTs are advantageous, at other place FETs are advantageous, but they will go parallel, and based on the specific application it can be used. So, we have discussed HBT and HAMT. So, here the basic structure of HBT and HAMT is drawn. If you see in HAMT, so we use a this is a nothing but NPN transistor. Now, NPN, the emitter is connected with N plus poly, and then there is a base which is P plus poly. So, on emitter there is a small there is a base after the emitter, and this is also part of the emitter. After that there is a collector which is going to collect the all the electrons. So, here the electron will move vertically. So, the electron transport will be vertically in a heterojunction bipolar transistor, and it has a we can also make the way we are making our MOSFETs, we can also make a HBT, silicon germanium based HBT. If this is a basic structure, if you are interested more in detail about understanding of HBT, how it works, I suggest to go for the references that we have provided, and you can study more in detail. Then another is a GaN HAMT. So, in GaN HAMT the electron movement will be horizontal, and there is a on the doped GaN there is a undoped GaN. So, because of these two doped and undoped, there is a 2 DEG gas layers will be made, and because of these 2 DEG, that is a due to difference in doped and undoped, this will have a well of electron will be made, and that electrons will move from one side to other side. So, it will improve the current density. So, amount of current density is increased because of this 2 DEG layer, and that happens because of the combination of doped and undoped material. Now, for the same GaN HAMT also, if you are interested to study more in detail about semiconductor physics of GaN HAMT, you can go through the reference material or the reference book that we have provided. So, this is all about the basic of transistors and HAMTs. So, we if you see we have just given the basic idea or the big picture that how what are the kind of devices that you can use for RF application. So, we can do the comparison. So, this is a comparison chart for a different device technology. in wireless communication or RF transceiver application. So, based on your requirement you can choose the technology that you want to go for. So, the parameters are listed here and then the technology are listed here. So, gallium arsenide based MESFET device speed is good. So, and even gallium arsenide HBT and HAMT. So, entire gas has a better device speed. Silicon RF CMOS has a fair speed compared to this, and HBT is a good, and indium phosphide based HBT is excellent in terms of device speed. Chip density in some of the lower node technology of RF CMOS, this we might get a higher speed. Then chip density, it is obviously low in the MESFET. In HBT it is high, gas HEMT it is low. Again silicon RF CMOS density is low, silicon germanium HBT it is high, and indium phosphide based HBT the density is high. Transconductance, obviously the transconductance is high in HBT and HAMT, and again in this silicon germanium. However, the RF CMOS has a lower transconductance. Device matching, it is better in HBTs. You will see the better matching that we have seen, because BJT has a certain input impedance. However, MESFET and HAMT has a poor matching. So, you required a good matching circuit on chip. 1 by F noise, again in HBT you can see that HBT does not have a that much, it has noise because it is mostly dominated by short noise. However, RF CMOS, gas MESFET or gas HAMT are poor. So, we need to be considered about while designing the circuits, the one flicker noise will be high, means the poor in FETs it is a high. So, then power adder efficiency, this gallium arsenide MESFET as and RF CMOS and silicon germanium HBT as a medium. However, gas and gas HAMT has a high power added efficiency. Even indium phosphide based HBT will have a high power added efficiency. Linearity, you can see that all the gas or other than RF CMOS all has a better linearity performance. The reason is the amount of voltage, because when we are going in RF CMOS for lower node technology and the VDD is reducing. So, as we are going for lower node, the VDD is reducing. So, the amount of time your signal, means peak to peak signal, V peak to peak will reduce, and that will reduce the linearity of your circuit. But for RF CMOS designer, it is a challenging task, and there are many good highly linear chips can also be designed based on improving the circuit architecture. So, that is why however, other material in other technologies the voltage is high, and that is why the linearity is better. Device matching, again this MESFET and HAMT as a poor, however, this silicon HBTs has a good device matching. Output conductance, it is high in RF CMOS, however, the other except MESFET all has a low loss. Now, if you see the integration level of out of all, the RF CMOS is the best, because it can be easily integrated with a complete backend, and we can have a very miniaturized small ASIC, and it will reduce the feature size of your complete components. So, that is why still we try to implement the RF CMOS high performance circuits, so that we can easily integrate it with a backend. However, other technology you require a 2 chip solution where front end will be made on the gas or indium phosphide or any HBTs, and the back end will be on the CMOS. But if you go for a RF CMOS, then all together you can make in a single chip. So, that is a biggest advantage of using a RF CMOS. And breakdown voltage can also be configured such that while making the device processes, we can have a medium, means moderate breakdown voltage. And possibly primary application, gas MOSFET are using VCO mixers and switches, RF switches. Gas HBT are used in power amplifier, pre-amplifier, means before that we already discussed the requirement of pre-amplifier in a transmitter to improve the linearity of complete transmitter and dividing the linearity among the each stages. Then gain blocks, oscillator amplifier, HAMT is used for LNA gain blocks and switches. So, there are many discrete components for testing and other application are used, and on that many companies are targeting this. For RF CMOS you require a back end logic control switches. So, company design can be made on the single chip. Silicon germanium HBT again low noise amplifier, power amplifier and gain blocks are used, and HBT means indium phosphide based HBT are used for LNA, power amplifier and VCOs. So, these are the basic comparison chart if you wish to design the any RF for any RF transceiver application, you can choose based on these devices. Thank you. We will continue with the same in the next class, active devices. Thank you all of you.